topic of this video is chapter 6.3, Hess's law. Hess's law is a very important natural law in chemistry that says that the enthalpy change in a chemical reaction, delta H, is a state function, which means that it depends only on the initial and final states and not on the particular mechanism or pathway of the reaction. It doesn't matter how you get from point A to point B, all that matters is the difference in enthalpy. Here's an example. The combustion of N2 to form NO is endothermic. Delta H is positive 180 kilojoules per mole of reaction. But the combustion of 2 moles of NO with another mole of O2 to form 2 moles of NO2 is exothermic. It has an enthalpy change of negative 112 kilojoules per mole. Well, if you measure the enthalpy change for the direct combustion of 1 mole of N2 and 2 moles of oxygen to form 2 moles of NO2, you measure the enthalpy change as positive 68 kilojoules per mole. Check this out. If I add the first two equations together and cancel what appears on both sides, namely the 2 moles of NO formed as a product in the first step and the 2 moles of NO used up as a reactant in the second step, I add them to get the third equation, and wouldn't you know, adding the two enthalpy changes for reaction 1 and reaction 2 gives you the enthalpy change for reaction 3. So it doesn't matter if it's a stepwise process or a single step, the overall difference in enthalpy is the same. Here's what it looks like on a potential energy diagram. If I start with, down here, 1 mole of N2 and 2 moles of O2, and I want to form 2 moles of NO and 1 mole of O2, I have to put in 180 kilojoules of energy. But then if I allow those 2 moles of NO to react with 1 mole of O2, I get out 112 kilojoules of energy, and what I see is that the difference is positive 68 kilojoules. So it doesn't matter whether I went the two-step process or the single-step process, the overall change in enthalpy is the same. So the question is, what do we do with that? Well, it turns out that Hess's law is dramatically useful because it allows us to determine the enthalpy change for a reaction that we cannot study directly. If we can manipulate equations for which we know the enthalpy change and add them together to get our desired reaction, then we can calculate the enthalpy change for that one. Now, what do I mean by manipulate an equation? Well, if we reverse the equation, we have to change the sign on delta H. Okay? If a reaction is endothermic in the forward direction, it must be exothermic in the reverse direction. If the equation is multiplied by some coefficient, we have to multiply delta H by the same coefficient. So, for example, we said that the combustion of N2 and O2 to form 2NO is endothermic. It has an enthalpy change of positive 180 kilojoules per mole of reaction. How would I determine the enthalpy change for the reaction of 4 moles of NO to form 2 moles of N2 and 2 moles of O2? Well, what did I do to the first equation to get the second equation? Well, clearly I reversed it and I doubled it. So delta H for the second equation is going to be negative 2 times positive 180 kilojoules per mole, or negative 360 kilojoules per mole. Okay? So let's look at using this method to determine the enthalpy change for a reaction that we cannot measure directly. Wow, a lot going on there. Okay? I've got 3 equations at the top, each of which involves the combustion of either a binary compound of chlorine and fluorine or of elemental fluorine to form oxygenated products. And I have listed the enthalpy changes for each of those reactions. It turns out historically a lot of this was done with combustion reactions because it turns out to be pretty easy to measure the enthalpy change for a combustion reaction. We want to use this information to calculate the standard enthalpy change for the reaction of 1 mole of chlorine monofluoride and 1 mole of elemental fluorine to form 1 mole of chlorine trifluoride, which it turns out you cannot do in a single step. So what do we have to do to get to this final equation? Well, the process I follow is I simply look at the goal equation that I've put inside a yellow box and ask myself, what do I have to do to each of the reactions above to get the reactants and products on the correct side? So for example, I want 1 mole of chlorine monofluoride on the reactant side. That only appears in the first equation, so I'm going to have to use that first equation, but it's got a coefficient of 2, so I'm going to have to multiply all the coefficients by 1/2. So that will give me ClF plus 1/2 O2 goes to 1/2 Cl2O plus 1/2 F2O. Now I'll list the corresponding enthalpy changes over here. Because I multiplied by the equation by 1/2, delta H here is going to be 1/2 positive 167.4 kilojoules per mole. Okay. I want to get now 1 mole of F2 on the reactant side. F2 only occurs in the third equation, and it has a coefficient of 2, so I'm going to have to multiply everything by 1/2. So that gives me F2 plus 1/2 O2 forms F2O. Again, the enthalpy change for this now will be 1/2 of the enthalpy change for the third reaction, which is negative 43.4 kilojoules per mole. And then finally, to get 1 mole of chlorine trifluoride on the product side, I'm going to have to use the second equation. But not only do I have to multiply it by 1/2 because it's got a coefficient of 2, but I have to reverse the reaction to get chlorine trifluoride on the product side. So doing those things gives me 1/2 Cl2O plus 3/2 F2O to form ClF3 plus O2. The enthalpy change for this now, because I reversed the equation and multiplied it by 1/2, I'll multiply the enthalpy change by negative 1/2 plus 341.4 kilojoules per mole. Now comes the fun part. Does it work? Well, if you paid attention to detail, everything that you don't want should cancel, and you should be left with what you want. I've got 1/2 mole of O2 plus 1/2 mole of O2 on the reactant side, 1 mole of O2 on the product side, so that cancels. I've got 1/2 mole of Cl2O on the reactant side, 1/2 mole of Cl2O on the product side, so they cancel. I've got 1.5 moles of F2O on the product side, and 3/2 moles of F2O on the reactant side. So I'm left with 1 mole of chlorine monofluoride and 1 mole of fluorine on the product side, and I forgot to cancel. Sorry, these cancel too, and 1 mole of chlorine trifluoride on the product side. So my reaction is ClF plus F2 forms ClF3. And to calculate the enthalpy change, I simply perform the calculation in the right-hand column, and I get the enthalpy change is negative 108.7 kilojoules per mole, which illustrates the power of Hess's law.